Well, hello there. Glad you could come. This is our first of many discussions which we'll be having about differential equations. Now, we could start by going through lots of definitions and terminology, but let's start with an example. Let's do something. So I have a simple question here. How does a spring move? And so I have as an example, I have a slinky with a clown nose, and we'll just add the clown nose here. That just helps us see a little bit better. And if we release it, we see this. And we say, well, what's happening? We're like, aha, it's going up and down. Brilliant, genius. So we've now answered the question. It goes up and down. But can we be a little bit more precise? Because when you say something goes up and down, there's a lot of ways it could go up and down. You might have it going up and down in some sort of a zigzaggy pattern. Maybe it goes something like this. Maybe it's doing something else. Who knows? Now, none of these feel right. If you ever thought about, well, when I think about a spring, that doesn't feel right for any of them. It feels like it should be something more along the lines of this. And you might even call it, there's a fancy word for it, sinusoidal. Say, okay, but how do we know this is a better answer than these answers? I mean, all of them are possible, but why is this one more probable? Can we figure that out? Well, of course, the answer is yes, and that's why we're starting here. All right, so to get to our answer, we start thinking about, okay, do we know anything about springs? And if we took physics and, of course, paid attention, of course, we all paid attention to physics, cool stuff. There's something called Hooke's law. Now, what does Hooke's law say? Well, it says, imagine that you have a spring, so we'll draw our spring here, and there's some sort of a resting state. Now, this is the spring if it's just in its natural state. So in its natural state, it doesn't want to go up and down. So let's see if we can get the spring to do that here. And all right, almost there. See how it's not moving? Now the question is, what happens if you take it and say pull down a little bit? What does the spring want to do? Well, it wants to go back. So there's something pulling it back up. There's a force. And if I were to release it, you'll see it goes back up. And similarly, if we were finding the resting state, it went too high, there's something that's going to pull it back down. So we say, all right, well, what's going on? So we take our same spring and let's stretch it. And so now we've stretched it, and there's this length that it's been stretched to. We'll call this x. Now Hooke's law says what? Well, it says that the further you pull, the stronger the force to pull it back. So in other words, if you start at resting state and pull it just a little bit, it's a small amount of force pulling it back up. But if you pull it a lot, and it's like, there's a lot of force pulling it back up. And it can be summarized as the following. Namely, we have that the force acting on the spring is proportional to, proportional is just a fancy way of saying that there's some constant, so some constant k, and times how far you've pulled it. Now there's one other piece, and that's because force has direction. And so if you imagine that you pull in the positive direction, the force wants you to move back, opposite. So there should be a minus sign. The minus sign basically says opposite. So force is minus kx, and this is Hooke's law. All right, well now we start thinking about, well, what's force? Well, force is, you can do it as mass times acceleration. Now, mass, that's easy, that's m. What is acceleration? It comes back to x. See, x is how far I pulled it. I can also think here of x as being position. All right, well, if x is position, what's acceleration? The first derivative of position is velocity, so the second derivative is acceleration. mx double prime equals minus kx. Or, just to simplify, we have that x double prime is equal to minus k over m times x. All right, so here we go. We started with just some very simple observations. We had Hooke's law, and we got to this equation. Now let's pause for a second and talk about what we have. Now I said the word equation, and so let's talk about what is an equation. So when we use the word equation, it means the following. It means that we have something equals something else. So that's what we have. So an equation is when you see an equal sign. So this is an equation. All right, well, great. Now, the topic of the course is differential equations. So what makes something a differential equation? Well, what's the word differential referring to? Now here, it turns out differential is referring to derivatives. So if you see the word differential, you just think, oh, you mean derivatives, right? Like, yeah, that's what it means. And so a differential equation says, aha, that there's a derivative involved someplace. So if you have a derivative involved somewhere, it doesn't have to be on both sides, it could be on one side, but as long as there's a derivative involved somewhere, then what you have is you might call it an equation with benefits, but we call it a differential equation. And so then this becomes a differential equation. So look at what we have. We wrote down that x double prime is minus k over m times x. It's an equation. There's a derivative involved. In this case, it's a second derivative, and therefore it's a differential equation. Now, why did we start by setting up a differential equation? Why not just say, aha, this is how the spring moves? Well, it turns out that oftentimes it's easier to describe how things change than to describe how things actually behave. So that's why we started with this scenario. We were able to say, aha, lo and behold, Hooke's law gives us a very nice way to talk about the way it's changing, the acceleration. And so we get this nice relationship. Now, what happens? Well, differential equations, the goal is to say, well, now let's figure out what x is. Once you set up your function, what should the x be that satisfies this kind of relationship? All right, well, how do we figure that out? Well, there's a lot of tools. And you might say, yes, but we don't know them. That is correct. We're going to learn them. That's the goal of the course. So let's start by simplifying. Notice we have this k over m, they're constants. Let's just make it really simple. Let's say k over m is 1. All right, so now we have x double prime is minus x. Now, the next thing we're going to do is look at our differential equation and start thinking, do we know any function that has this property that when you take two derivatives, you get back what you started with, except there's a minus sign? Now you might say, ooh, e to the x, right? Well, e to the x, what happens is, take one derivative, you get e to the x, take it again, you get e to the x. E to the minus x? Well, you get a minus the first time, but another minus the second time. And in math, two wrongs make a right. Wait, no. Two negatives make a positive. But of course, we don't have to imagine too long, because we know that there are some functions that have this behavior, and they are sine and cosine. So we say, ah, this looks like sine, or it looks like cosine. And so then we can say, well, actually, really, it could be either one, sine or cosine, or a combination of the two. So our great aha says, oh, x looks like something sine plus something cosine. So if you take this derivative twice, and we can do that, so the first time you get a cosine t minus b sine t, and the second derivative would be minus a sine of t minus b cosine of t. And lo and behold, what do you see? Well, it's the negative of x. So that says that this is the solution, which means that this curve that looks like a sine curve really is the right way to talk about how a spring moves. It really does follow that. And it turns out, we don't know this yet, but we'll see, every solution to x double prime equals minus x has this exact same behavior. And so we've employed a technique. There's a mathematician named Polya who said the way to solve a differential equation is to stare at it long enough until a solution occurs to you. Well, maybe, but oftentimes it's better to have tools. So we're going to be developing tools, and we won't have to rely on good guessing. Now, keep in mind, good guessing is actually very valuable, a very useful and wonderful technique in trying to figure things out. I am a fan of having a good guess. All right, so there we go. We were able to answer how does the spring move, and what was the process? Let's just recap it. We said, okay, we start with some basic properties of springs, Hooke's law, turn that into a differential equation. Remember, that's where we have something equals something, where derivatives involved. And then we said, all right, let's look at a special case and see if we can figure it out. And we saw, aha, sine and cosine. Great. Now we have our answer. All right, well, this seems pretty easy, right? Great. There's nothing challenging. Well, we had a fairly simple differential equation here. What if we changed it ever so slightly? Say we said x double prime equals minus x minus 0.00001 x prime. Or we had x double prime equals minus x plus 0.0001 x prime. Now, what happens? Not so clear, is it? But we'll be able to answer this kind of question in the not too distant future. By the way, does it make a difference? This extra piece we're adding on or subtracting on? Well, maybe. In the very short term, no. The perception is the difference is so tiny, we would rather have it be a rounding error. But in the long term, and after all, isn't that what we care about? The long term? We'd see that one of these would have a spring that would very slowly calm down until it was barely moving. And the other one would be going crazy and probably break. And so yeah, it can make a difference. One other thing to mention before we move on is this is an example of one of the things that differential equations works really well on. And namely, whenever we have something that's oscillating. So if you ever think about oscillating systems, of course, springs oscillate, but lots of other things oscillate. Vibrations in the wing of a plane. Yeah, you might want to be able to model that and understand what's going on. There will be a couple of other things that we'll see where differential equations come in really well, namely understanding growth, how things expand or contract, and mixing, how things come together. And so this growth you might see in population studies, mixing you might see in chemistry, how do certain chemicals come together, what proportion of the chemical is there after a certain amount of time. And so these are our three go-to examples. And oftentimes, a lot of the things that you look at in the world around you, you can think of as sort of some combination of these things. Is it vibrating? Is it growing? Is it mixing? And oftentimes, if the answer is yes, then there's a differential equation lurking in the background. So we mentioned what a differential equation is. An equation where there's a derivative involved. Now, it could be first derivative, or second derivative, any order derivative we want, actually. And we're going to keep things simple here, or ordinary. So when we talk about ordinary differential equations, we're looking at functions of a single variable There are other topics. There's something called partial differential equations, where you have functions of several variables. That's not this course. It's a very beautiful topic, and of course, if you like differential equations, I would encourage you to pursue learning more about that. So I just want to look at a few examples that we have of differential equations. So here we have dx dt, that's x cubed plus xt. Here we have the second derivative of y with respect to x minus 5 times the first derivative of y with respect to x plus 6y equals 0. Here we have y double prime minus 5y prime plus 6y equals 0. And you might say, wait a second, deja vu? Yeah, they are. This is really the same differential equation, but the thing is, different notation. So be on the lookout for that. There's lots of different notations, so make sure you know your notation, and don't be like, I'm going to be beholden to one or the other. Sometimes we won't write dy over dx. We'll separate the dy and the dx, and you could argue that's a little bit of a bad form, but there's reasons why mathematicians would do that. And so you might have something that says 2xy dy plus y squared dx equals sine of x dx. And of course you can get very complicated. Y prime plus arctangent y prime equals 1 over x squared plus 1, hopeless. Terrible. As much as I love arctangent, this would be a hard one to solve. Hard meaning, no, we're not going to do it. But even if you can't solve a differential equation, you can still talk about numerically what it looks like, and we'll get to at some point in the semester talking about numerical approximation. And this is actually a big way that differential equations are now done. I mean, a lot of times when a computer solves something, it doesn't try to solve it exactly. It says, look, I'll give you a really good approximation, good enough to be in the time span that you're interested in. Now, here's another differential equation. Y prime equals e to the 2x plus 6 cosine 3x. You're like, whoa, that doesn't seem that tricky. That seems like stuff I've done before, because we've done it before, right? Yeah, this is like Calc 1 stuff. And you say, oh, well, can I just solve it using Calc 1 tools? Yes, you can. Let's solve it. Might as well get some practice in. So how do we solve something like this? Okay, well, we can just integrate both sides. Say, all right, integral of y prime. Now, integrating a derivative, easy. That would be y. Integral of e to the 2x. Well, it's e to the 2x. And then what goes in front? A half. Good. You divide by that 2. Integral of cosine. Well, there's a sign. Positive or negative? Positive. All right. What goes in front of the sign? The inside is still 3x. In front is a 2. Because you still have the 6, but then you have to divide by the 3. So we have plus 2 sine 3x. Are we done? Nope, there's plus c. All right, good. Wow, we're differential equation solving machines, right? Cool. Now, we should, of course, make some observations. We will keep getting consistently these plus c's. They're important. Essentially, the plus c says, well, there's not a unique solution. There's a range of solutions. And now we say, okay, but maybe we have some extra information. We call those initial conditions. That lets us solve for c. Now, another thing that you might say is, oh, whoops, we could be in trouble here, because we know from Calc 2, if not beforehand, that even just things of the form y prime equals function of x, that can be pretty tricky, if not impossible to do explicitly. So there's definitely going to be a lot of work involved. And the other thing, of course, you might say, well, why can't we just do things like that up here? Why can't we integrate both sides? Well, the problem is, when we did this integration, we integrated with respect to what? Well, we integrated with respect to x. So we should have put a dx here. When you integrate up here, what do you integrate with respect to? You integrate with respect to t. And you say, all right, great, this side, pretty easy. But what's the integral of x cubed dt? Good luck. It's not 1/4 x to the fourth, because I'm not integrating with respect to x, I'm integrating with respect to t. And that's why we'll see these can be much, much more challenging. But most of these, at least several of these, are very doable. And we'll be able to do them as we go on. All right, so let's just wrap up for now with sort of a look ahead. What are we going to be doing? Well, roughly speaking, we split the course up into 3 parts. And in the first part, we're going to talk about our starting is what we call first order differential equations. Now, when we talk about order, that's referring to what kind of derivative are we dealing with. So first order differential equations means that we're going to be dealing with things where there's just a single derivative involved. And we say, all right, great. Can we handle that? And we'll see that there are some tools available to us, again, with limitations. And then we'll get into second plus order differential equations, and we'll look at these. Now, we're going to see that our tools are going to become much more limited, so much so that we're really going to narrow our focus down primarily on a very special type, and that is what we call linear. Now, linear is just a fancy way to say it works nicely with adding and scaling. We'll get into that later on. Well, then we're going to transition to the second part of the course. And the second part of the course is when we have what we call systems. And that means that there are multiple things changing at the same time. And for this, well, we're going to hang out and spend some time working with matrices. And so that'll be a lot of fun. Because who doesn't like a good matrix? I know I do. That brings us to the last part of the course, which we're going to talk about Laplace transforms. And Laplace transforms are actually a fun idea. It says, hey, let's take our differential equation and then we're going to turn it into an algebra problem. And then why is that helpful? Well, because hopefully by now we're good at algebra problems. So we take our differential equation, turn it into an algebra problem, solve our algebra problem because we're good at it, remember? And then we go back and say, aha, there's our solution to our differential equation problem. And there's a nice relationship. And the transform is what allows us to get from one to the other. And of course, our last topic we're going to have some fun is series. And so if you remember from before, calculus, what is a series? Well, it's something that looks like a sum ck x to the k. And this is a great way to go about finding good approximations. One of the punchlines of calculus too is that, hey, every function looks like a polynomial. And a series is just saying, hey, this is a big polynomial. And so, well, what do we need to figure out? What are the coefficients? And so talking about finding series solutions really means saying, what are the right CK? So that's where we're going. And it's going to be a lot of fun. So keep coming back. And I look forward to spending more time with you in the next few months. All right. Take care. Bye.